Hi guys, in today's video we're going to take a look at reactions of alkenes, so carbon-carbon double bonds. Remember when we talked about the structure of alkenes, they have this extra pi bond with these sort of perpendicular orbitals, the pi orbitals that have electrons that are being shared through space. It's actually those electrons that, because they're not as strongly bound as a regular head-on bond and a sigma bond, those electrons are more available for reactivity. So that helps explain why alkenes actually are much more reactive and quite a bit more interesting actually than regular old alkanes. All right, so the first type of reaction we're going to take a look at is the symmetrical addition reaction. And this is where you use a reagent that's going to add identical atoms to the carbons of the double bond. So if I just were to write a generic reaction, so let's just use a very simple alkene. We use ethene. Okay, so if I were to use this and react it with a reagent, we're just going to call X2. All right, we'll talk about what X can be here in just a second. If you mix these together, the two atoms of this X2 reagent are going to end up adding to the two carbons of the ethene. And what's going to happen is that the double bond is going to be removed. Okay, so notice in the starting material, the ethene, we had that carbon-carbon double bond. But now when X2 adds, it's going to add essentially across the double bond, adding the two X groups. And notice now the double bond has been removed. An important caveat of this reaction is we've gone from a starting material that has bond angles of 120 degrees to now this shape, which is tetrahedral, 109.5. So when alkenes react in this fashion, the shape of the carbon skeleton is actually going to change. So what exactly can X2 be? Well, there are a whole host of reagents that could actually do this, but in our class and in our discussion, we're going to be focusing on just a few of them. So some halogens, Cl2, Br2. Okay, those are the main halogens that will react. You could use I2, it's not quite as reactive. And fluorine, or F2, is virtually unreactive for this type of reaction. You'd have to add a catalyst to that. Another type of X2 reagent is hydrogen, H2. But when we do this, you have to add a catalyst. And usually that's going to be a metal. And the metals that are often used are nickel, platinum, or palladium. Now these two are quite expensive. Platinum and palladium are quite expensive, but nickel is a relatively inexpensive catalyst. So basically all of these X2 reagents, you could basically substitute this in right here. They're going to add the two the two atoms across the double bond. So let's take a look at an example of an actual molecule and have it react with some of these X2 reagents. So what I'll do is I'll draw these out in a way that we can basically use the same starting material. So this compound is called 1, 2, 3, 4. This would be 1-butene. Make sure you're not calling it 1-butene. That's a no-no. So 1-butene. And let's use that same starting material for the various reagents that we talked about. So Cl2, Br2, and H2 with some catalyst, usually a metal catalyst, as I mentioned before. So in order to draw out what these now are going to look like, we're essentially going to redraw the carbon skeleton here, but just now insert our two atoms of the X2 group and remove the double bond. So in all cases, all we have to do is just redraw a butane chain. And now let's add our reagents. So here we would have a chlorine that's here and a chlorine there. Okay, so we now have synthesized the molecule 1,2-dichlorobutane. In this case, we'd add bromines, same way, and we would now have 1,2-dibromobutane. Now in this case, we are doing the same thing, but I actually am not even going to draw in the hydrogens because there's an implied hydrogen here. There's two implied hydrogens at carbon 1 of the starting material. So if we add the two hydrogens, they would both be sticking off of there, but I'm just not going to draw them. So we would just get butane as our compound as a result of that. So moving on to the next type of reaction that alkenes can undergo. This is what's called the unsymmetrical addition reaction of a different type of reagent called HX. So if I were to draw out, again, a generic carbon-carbon double bond, let's use ethene again. And I'm now going to add a reagent called HX, and I'll list out what X can be here in just a second. Kind of like we saw before, these two atoms, the H and the X, are going to add across the double bond, again changing the shape of the carbons from being 120 degrees, oops, again the bond angles here are 120. When HX adds across the double bond, we change the geometry of these, again, to become tetrahedral, 109.5. And we've now added H and X across that double bond. So what can HX be? All right, so HX can be HCl, HBr, okay, so hydrochloric acid, hydrobromic acid, but it can also be water, HOH. So notice our X group is OH. Now when you do add this, you have to add an acid catalyst. So those are the three main types of reagents that we'll take a look at a couple examples of this. The one for allied health chemistry that's the most important is actually going to be water. So the addition of water to a carbon-carbon double bond we'll see countless times when we get into metabolism. This is a very common reaction that will occur in the body. So let's take a look at a molecule that has a carbon-carbon double bond in it and see how it would react with some of these HX reagents. So I'm going to start with this compound, cyclohexene. And again, I'll use sort of this diagram where I'm going to list out the various reagents all reacting with the same molecule. By the way, this type of diagram is often called a spider diagram or a reaction spider diagram, very commonly used. So let's add HCl, HBr, or HOH, or water, with an H plus catalyst. By the way, the H plus catalyst, it sometimes will be written out as that, but more often than not, it's going to be H2SO4, which is sulfuric acid. You could also potentially use phosphoric acid or some really strong acid, but it's just going to be added in a small catalytic amount. All right, so going back to our HX reagents, again, we're going to be adding the two atoms of H and Cl across this double bond. So the cyclohexene now is going to have its double bond removed, and now we're just going to put chlorine and H right there. Okay, so again, the double bond is removed. We've changed the geometry of these to be 109.5 degrees. Okay, likewise, HBr would look like that. Now notice I added the bromine to this lower carbon and the hydrogen over here. I could have flipped it either way. Because this is a symmetric starting material, it would be the same compound. I would get one bromocyclohexane whether I added it here or here. Same thing with the chlorine. Doesn't really matter in this case. In the upcoming video, we're going to see what happens when you actually have a little bit more complex starting material that's not symmetric like this. Notice this has sort of a plane of symmetry through it, so both of these carbons are equivalent. So you would get the same product when you add HX across. So lastly, we would convert the cyclohexene molecule if we added water to the double bond. We actually convert the alkene into an alcohol. So this would be cyclohexanol. This is a very, very important transformation. The conversion of alkenes into alcohols is one that we'll see time and time again as we go on.